So welcome back. So this is local search part 4, and we are not yet there. There are many more. But this lecture is really interesting. And the reason it's interesting is that we are going to look at optimization under constraints and how we can do local search on this. And why is it interesting? Because there are many, many, many options. There are many ways you can actually approach this, and there will be different trade-offs in the complexity of the neighborhood and the complexity of the objective function, the complexity of the search. So we're going to illustrate every one of these various possibilities using graph coloring, which is very simple to conceptually, but it's a very, very hard problem to solve very large instances. Remember, graph coloring, this was the city of Europe that we saw when we were doing constraint programming, okay? So we can model that as a graph, right? So every country would be essentially associated with a vertex, and then there will be an edge between these two vertices if the two countries are adjacent. Okay, and now the goal of the application would be to find a coloring of this graph such that every two vertices which are adjacent are given a different color. Okay, so that's graph coloring at a high level. Now this is a tiny, tiny, tiny little graph. So what we are really going to be talking about here are really huge graph. Okay, so this is 250 vertices. It's a graph which is generated randomly, and the probability of having an edge between two vertices is 10%, is 0.1. Okay, and so you can already see how dense it is. Okay, and one of the key things about graph coloring, which is nice, is that random problems are typically very hard. So if you take, let's say, 250 vertices, 0.5 density, that's a really difficult problem. Okay, so this is the kind of things that we want to tackle. Okay, so color me this graph and find me the smallest number of colors, okay, to color this graph. Okay, so there are two aspects, of course. Okay, so one aspect is that we have to minimize this number of colors. Okay, we want to use as few colors as possible. But there is also the feasibility axis. At any point, we want this coloring to be legal. Two nodes, two vertices that are basically adjacent to each other should be given a different color. So there is a trade-off between these things, and how we're going to deal with that. Okay, and that's essentially the topic of this lecture. How can we balance the fact that we want to decrease the number of colors, but we want also to get a feasible solution. Okay, and so essentially the way we're going to combine that in local search, there are basically three ways. The first one is just to say, what I love in life are feasibility problems. So I want to reduce that problem to a sequence of feasibility problems. I only want to solve feasibility problems, and I will show you how to do that. Okay, then the other things, and this is essentially what we have done already for the traveling salesman problems and also for the warehouse location, we can decide that we will stay in the space of feasible solution. We will only look at legal coloring, so no violations of the constraints ever. Okay, and you'll see that this is actually raising some interesting challenges, and we'll see how we can address some of them. Okay, so then essentially the last thing is like, well, I don't want to look at this as a feasibility problem, okay, because it's both a feasibility and optimization problem. I don't want to stay, in the space of feasible solution, because once again, I want to deal with both aspects. And so what you're trying to do is basically look at both aspects simultaneously, and you will consider both feasible and infeasible configuration. So you will be in a larger space, okay, so you will both consider feasible and infeasible solution, and we'll try at the same time to decrease, to minimize the objective function, but also to find feasible solution. And I will show you how we can do that. And in graph coloring, there is a beautiful way to do that, which is really nice to explain. Okay, so let's start with looking at optimization as feasibility. Okay, so I told you we are obsessed with feasibility. Every optimization problem, we want to take it and view it as a sequence of feasibility problem. How can we do that in graph coloring? This is what we do. We start with a feasible solution with a certain number of colors. So you can take a greedy algorithm and just try to find a feasible solution. And let's say we have k colors for that particular solution. Okay, so once we have this k color, we say, okay, so the next problem should have at least one fewer color. Okay, so we want a solution, let's say, with k minus 1 color. Okay, what do? Well, we take all the vertices which are, let's say color with color k, and we basically replace them with a color which is from 1 to k minus 1. Okay? Now what do we have? The problem is infeasible. We have plenty of violations, right? Or maybe not, but we have, most likely we'll have violations. So what you do is we say, okay, so now the goal is to find a feasible solution with these k minus 1 colors, okay? And then obviously, once we find a solution to that, okay, so we start with k minus 2, k minus 3, and so on and so forth until we cannot find a feasible solution to a problem, in which case we know that we have an optimal solution, except that here we'll be using local search, so we will have no guarantees. Okay, so the key questions here is obviously, okay, so this is easy to do, but how do we find a feasible solution? Okay, when, how do we, find a feasible solution, let's say with k minus 1 color? And the way you can do that is essentially what we did in the first 2 lectures on graph coloring, right? So you look at the problem, you look at the violations, and you try to minimize this violation, okay? So we have seen how to do this, okay? So we just do that, okay? And that's the first approach for solving optimization problem, okay? Very much like the way constraint programming solves optimization problems. So you view that as a sequence of feasibility problem. At every one of these steps, you try to minimize the number of violations, and then you have a feasible solution with k minus 1. You do the same with k minus 2, and so on and so forth, okay? So that's that's the first approach. The other approach is to say, I don't like feasibility problems. I'm always going to assume that I'm feasible, okay? And I'm focusing on the objective function only, okay? That's what I'm obsessed about, okay? So what do we do in graph coloring? Okay, so the objective function is going to be minimizing the number of colors, and you assume that all the configuration is basically satisfying all the constraints, okay? Now, how to guide the search? That's the problem, right? So because essentially it's like in the magic square example, right? So now we have all these legal colorings, okay? And now we're going to change the color of one particular vertex, but how is that going to affect the number of colors that we have? Most likely it will not do anything, right? Because if you could remove that color and, in one step and get a solution, that would be kind of a very unlikely event. And now you probably have a lot of colors with k minus 1, okay? And you will have to get rid of many of them. But changing one is not going to change the number of colors. So the number of colors is kind of a very coarse way of looking at the objective function. So what you have to do is essentially change the way you think about the problems and the objective function, okay? And this is where introducing the concept of color classes is useful, okay? So essentially what I'm going to say is that color class I, Ci, is going to be the set of vertices which are color with color I, okay? So essentially Ci is all the vertices in my huge graph, okay, which are color with color I, okay? So C2 is all the vertices color with 2. Okay? And now, to drive the search, I'm not going to look at how many colors I'm using. I'm going to look at a proxy, an indirect way of trying to minimize the number of colors. Okay? And the way to do this is to look at the color classes and try to have huge color classes, right? Because, when you use very few colors, typically you have large color classes. Okay? So this is the optimization function that we are going to use. It's an indirect objective function. It doesn't directly minimize the number of colors. Instead, what it's trying to do is to minimize the square of the sizes of the color classes. Okay? So in a sense, what I'm saying, I want big classes. I want big classes. Okay? And so think of it, if there is one class with one color and another class with 10,000, one vertex, and another class with 10,000 vertices, if you move one from the other, for the large class, you're going to have a really big increase in this objective function where you maximize the size of the classes. Okay? So this is what we're going to do. Okay? Now, once you do that, okay, so one of the problems that you may have is that it may be actually very difficult to move from one legal coloring to another one. You may be really, really heavily constrained by the fact that you're working in the space of legal colorings. Okay, so in a sense, in many of these applications, okay, so once you are trying to keep the constraints feasible, you have to think of a neighborhood that allows you to actually explore legal colorings in a reasonable fashion and move, to places, okay, and not being stuck in a particular configuration where there is no way to move because I would violate at least one constraint, okay, and this is an idea that you can actually use inside inside coloring, okay? So it's a richer neighborhood, which is exploiting the structure of coloring much better, okay? And this is called Chemchain, okay? So let's look at two color classes here. You have the, CI and CJ, okay? And look at one of the vertices here, V, okay? And assume that you want to change the color of V, to blue, okay? It's red right now, it has to go to blue, okay? Now, it's very difficult to do that right now, right? Because essentially, what you see is that V is connected to these three vertices which are already color blue, okay? And therefore, if you color V to blue, you will have three constraint violations, and you can't do that, right? So we are in the space of legal colorings, okay? So what are we going to do? Well, an idea would be to say, oh, what I can do is take this guy and move it to the other side, but then I take these three guys which are blue and I color them red. Okay, so these guys have no violation these guys have no violations between themselves, so you move them together. Okay, but then what is the problem? Okay, so this guy here, is connected to another guy which is red. So if I move this guy to the other side, I have to do this guy and move it to the blue side. Okay. Oh, but this guy is also connected to this blue guy, so I have to move this blue guy on the other side and then move this red guy to the other side. And that's the idea of Chemchain. So you look at these these connected components, and you take all the components that are connected there, and you move them. You move the red to the blues and the blues to the red all together. Okay. So you basically select all these connected guys. Okay, that you see. Okay, and then this is basically the various components, the various vertices here that are connected. And you take the red one, you make them blue. You take the blue one, you make them red. Okay, and you swap them essentially. And that's what you get. And now, magically, I mean not magically, by design, right? So what we have here is that all the vertices that are blue, have no violation. All the vertices that are red have no violations. And obviously, you still have the links between the red and the blue. These are basically the same links than before. Okay, so this is a much richer neighborhood, right? So you take a vertex, okay, and you take a color class in which you want to move that vertex, and then you find this component and you swap these two sets of vertices. Okay, much richer neighborhood, but the beauty here is that we are staying in the feasible space. Okay, so all the colorings are always going to be legal, and therefore we can only focus on the objective function the same way as I have shown you when I was just swapping the color of a particular vertex. Okay, so it's a much richer neighborhood. I can explore many more things. Okay, so the neighborhood is much larger, and therefore in general the quality is going to be better. Okay, so we have to deal with the efficiency side, but in a sense, the neighborhood, by definition, is going to be better, but you're still feasible, and this may be very interesting. Okay, so we have seen two approaches so far. The first one was looking up. In the first one we were obsessed with feasibility, and we're trying to solve this sequence of feasibility problems. In the second one, we were obsessed with the objective function, and we always stayed feasible and try to improve the objective functions. Okay. The third approach is to say, okay, so I'm not obsessed by anything. I'm going to look at feasible and infeasible coloring. I can be both feasible at some point in the search and sometimes infeasible as well, right? And so now the search will focus on two things at the same time. We will have to focus on decreasing the number of colors, and also we'll have to focus on decreasing the violations of the constraints, trying to ensure feasibility and find a legal coloring. Okay, so how do I do that? Typically, what I want is an objective function that balances the two things. Okay, so I want to have something which looks at the objective and weight it. Okay, and I want to have something which looks at the violations of the constraints and also is associated with a particular weight. And what I minimize is the overall thing. Okay, so in a sense, sometimes I'm favor the objective function, and sometimes I'm favor, the feasibility, and the objective function is going to basically drive me to something which is good in both sense. Okay. So what is the neighborhood that I'm going to be concerned with here? We're going to take a very, very simple neighborhood. This is only changing the color of a vertex. Okay? And then I need to introduce another concept such that we can express the joint objective function nicely. I'm going to talk about bad edges. Okay? And a bad edge is simply an edge between two vertices, okay, which are colored with the same color. So these two vertices are linked. Okay, they have the same color, so the edge is called a bad edge. Okay, so it's a violation essentially. Okay, and I'm going to denote bi. Okay, the set of bad edges which are color with color I. Okay, so I have two edges. So for having a bad edge, I need these two vertices to have the same color. Okay, if that edge is considered a bad edge of color I. Okay, I'll look at all my graph and I'll look at all the vertices which are connected to all the vertices, two vertices that are connected by an edge, and I color by I. I know that these are basically violation, and BI is the set of those edges. Okay, so concept of bad edges. Okay, and now essentially what I want to do is find a nice way of expressing this objective function. Okay, once again, neighborhood is changing one color. Okay, now I have to focus on the objective function. I'm going to use exactly the same thing that we have done when we were in the feasible space. I'm going to try to maximize the square of the sizes of the color classes. Okay, so that basically drives me towards coloring with very few colors. And then I have to remove the violation, okay? And the violation can be expressed very simply, right? So what I want to do is to minimize the sum of the bad edges, okay? So the sum of the sizes of the set of bad edges. And that's what you see over there. So what I have to do is maximize this, minimize this, and I can combine these two, okay? So and the way I'm going to do this is by using this objective function. Okay, so it has the two aspects that I've mentioned before. Okay, so we are basically here, maximizing the sizes of the color classes. Nothing fancy there. Okay, since overall I'm minimizing. Okay, so maximizing this is basically a minus of this. Okay, so that's easy. And then the other things that you see here is essentially this is the part which is minimizing the violation. Okay, and instead of simply the sum of the sizes of the bad edges, the set of bad edges, what I'm doing here is multiplying this by the size of the color classes of these edges, and then multiply the whole thing by 2. Okay. Now you may say this guy is completely crazy. Okay, but essentially there is a good reason to do this. Okay, so this objective function has the beautiful property. Okay, so, and before I tell you what that property is, okay, so one of the things you have to think about is when we are trying to minimize these two components, together, okay, so let's say the objective and then feasibility, okay, the local minima have no guarantees whatsoever on what this objective function is going to be and how the two aspects are going to be combined together, right? So you have no guarantees that when you reach a local minima, okay, so you actually have a feasible solution, okay, a feasible coloring, okay? So in a sense, you don't know at that point that this minima is actually giving you a solution to your problem. Okay, so what this objective function here does for you is that it guarantees that local minima are going to be legal coloring. Wow, that's amazing, right? So I just minimize this function using local search. I get to a local minima, and because of the design of this function, you are guaranteed that minima is going to be a legal coloring. Okay, and therefore, you can just run this thing, find a local minima or find a bunch of local minima, and all of them will be legal coloring, and you can take one of them, okay, as your solution. Okay, and why is this true? This is the proof. It's a very simple proof. Okay, and the key idea of the proof is, okay, so let's assume that I have a coloring. Okay, in color class C1 to CK. So I have K colors. Okay, and I'm going to assume that I have a violation. Okay, so that means that one of the BI is not empty. Okay, so I have a bad edge somewhere, and let's assume that this is color I. Okay, and what I'm basically going to show you is that this particular configuration, okay, is not a local minima. It cannot be a local minima because I can improve it. I can improve it by changing the value of a single vertex. Okay. So what I do is that I'm going to add a new color, K+1, and then I'm going to select the bad edges in BI, and I'm going to select a vertex in that particular edge, okay? And I'm going to change the color of that vertex from I to K+1, okay? And I'm going to show you that the value of the objective function is going to decrease, and therefore this cannot be a local minima because I do this local move and I have a better solution, okay? And so by definition, therefore, all the local minima are going to be legal colorings. Okay, so how do we do that? Well, you look at the objective function, right? And the only thing that we have to do is to see how it varies. Okay, and typically there are these two, there are these two parts of the objective function, and we're going to analyze them separately, right? So how does it vary? Well, with the left term, okay. So if we go back, the left term here is basically the term dealing with feasibilities. Okay, so this. this term essentially varies in this particular way. So this is the value before the local move that I'm making right now. This is the value after, okay? So what I do there is that I decrease the bad edges by 1, and I also decrease the size of the color classes I by 1, because I move the color to k plus 1, okay? And so therefore the number of bad edges for this is the number of bad edges that I will get, okay? Of course the new edge, you know, the vertex that I selected will have no violation because it's a new color that nobody else is using, okay? So I do some algebraic manipulation, and you know that this thing is going to be, you know, basically the decrease in this left term is going to be greater, actually it's going to be equal to 2 times the size of Ci, okay? So, you know, this is how the left term is basically varying. Now, you look at the right term. The right term is looking at basically the objective part, the size of the color classes, okay? Now, it's, you know, in the formula, it's negated, right? So what we have to study is how this, you know, right term increases, because there's going to be a decrease in the objective function, an increase in the, well, it's going to be an increase in the objective function. So what we do there, we take, you know, the square of the class is I, because that's the class which is decreasing. The new configuration will have 1 fewer vertex there, but we'll have also 1 more color classes, which has a value of 1. You know, you manipulate this and you get what? 2c, you know, size of Ci minus 2. And that term actually is smaller than the term that we saw over there by 2. So we know that the objective function in this particular case is going to decrease at least by 2. Okay? So which basically means that if your coloring is not legal, I always have a way to decrease the objective function by 2. And therefore, this is not a local minima. Okay? So the beautiful objective function that I've shown you has this beautiful property, okay, that, you know, it will give you, every kind of local minima will give you local coloring. So once your search terminates, you don't have to worry. You will have a solution to your problem with a small, well, hopefully a small number of colors. Okay? So essentially, let's try to summarize what we saw here is that when you have an optimization problem, okay, which combines the objective function and a set of constraints, there are 3 ways to look at it. Solving a sequence of feasibility problem, or focusing on the objective function and always staying in the feasible space, or trying to basically balance the search in the feasible space and the infeasible space, and hopefully, you know, having some properties or some techniques that will guarantee that the local minima are going to be feasible solution. So the rest of the lectures are going to focus on some more complex neighborhoods and also on how to escape local minima. Okay? Thank you.